Hello friends, today we are going to discuss about single phase full wave rectifier with midpoint connection for an RL load. Friends, as we all know about a single phase full wave rectifier for only a resistive load, so we all saw how the waveform varies and how the voltage and the current appear across the output or the output load register. So today we are going to discuss about what happens in case of a resistive and inductive load. So we will be taking a midpoint connection of a full wave rectifier, and we will be connecting a resistive and inductive load across it, and finally we will be looking forward to the output waveform of the voltage and the current of a full wave midpoint rectifier. So first of all, let's talk about the circuit diagram. So friends, I am going to take a AC source through a transformer, primary and secondary. So first of all, I will be connecting an AC source to the primary coil of a transformer, and through the secondary I will be taking a midpoint connection, and through that I will be connecting a rectifier connection to the resistive and the inductive load. So let's see how it works. So friends, as you can see here, let Vs be the input AC source which I have connected to the primary of this transformer, and to the secondary I have taken a midpoint connection where there are two thyristors. Say this is T1 and say this is T2, and there is a load connected to it. In this case the load is an RL load. Now friends, whenever we connect an AC voltage to the primary terminal of the transformer, first of all, if you can see, there is a small difference here where in the earlier lectures, whenever we were talking about the full wave rectifiers, we used to connect diodes across the load. But here, in this case, we are connecting two thyristors, which are T1 and T2. So here you can see there are two thyristors, one is T1 and one is T2. The reason being that in case of a diode, as you all know, diode is a uncontrolled device. That means it allows the direction of flow of current only in one direction. However, thyristor is a semi-controlled device. So if a semiconductor device is semi-controlled, that means we can control the voltage across it, or we can control the flow of electric current as per our wish, just by changing the gate terminal, or just by changing the gate supply to the thyristor. Now friends, if you can see, so this is the first gate terminal of the thyristor T1. Let's say this is G1. Let's say this is the second gate terminal of the thyristor T2, which is G2. Now friends, if I control the gate current or the gate voltage so that I can decide when my thyristor, they will be starting conducting the flow of electric current. First of all, if a load is inductive or a resistive and inductive load, remember one thing, the current rises or falls slowly. That's a very important point that we have got to remember. So whenever an inductive load is connected, the current rises slowly and it will fall slowly as well. And let's say there will be some conducting angle as well, because we are dealing with the thyristor. So these are the summary of what we are going to do in next. So now we will be discussing about how this works. Now friends, if you can see, whenever we are giving a sine wave to the primary terminal of a transformer, first of all, the positive cycle, or during the positive cycle, T1 will conduct, and during the negative cycle, T2 will conduct, and the flow of direction, or the direction of flow of electric current through the load will be the same. For example, here during the positive cycle, if we talk about this loop, this will be the flow of electric current, let's say I, And during the negative cycle, again, this will be the flow of electric current, because if I give a direction through the coupling of these two coils, the direction will be so we all know the dot convention of a transformer or an inductor. So this is how the direction that we decide, through the dot convention. Now friends, as we all can see, the direction of electric current through the load is always the same. So during the positive half cycle, if it is clockwise, during the negative half cycle, this will be anti-clockwise. But however, through the load, if you can see, the direction will always be the same, from right to left. Now friends, we all could see that it is rectifying the input AC supply through the midpoint connection. So obviously the output voltage will be a pulse rated DC voltage. Now let's talk about what will be the output current, how does it look like, what would be the output voltage, how does it look like, and what happens to the current charging and discharging to the inductor. Overall, we will be looking forward to the output current waveform and the output voltage waveform. So friends, let's say if I have to draw the input voltage or input rectified voltage right on the secondary terminal of a transformer, it looks like this. Let's say the peak of this waveform will be VAN through one cycle, and through the second cycle, let's the waveform be this one. Let us say this is VBN. Now friends, let's do one thing now. Suppose we will be giving a gate supply to thyristor T1 after at certain interval of time. Let's say the conduction angle of thyristor T1 would be alpha. Okay, so if we can again say in the same circuit, let's say this is IG1. If I take IG1 on the y-axis and I'm drawing the same thing and I'm taking time in the x-axis. Okay, so here friends, I just forgot to mention one thing here. This is the time axis, so x-axis always is the time axis, and this one, the y-axis, would be the voltage of the input. So I'm writing V in. Now friends, if I say that alpha is the conduction angle, so here let's say at this specific point, which is alpha, I gave a input gate current to the thyristor T1. So I am drawing the input gate current pulse. So again, so at this point, that would be the same input gate current pulse. So now friends, at this point, T1 will start conducting. So if we draw that waveform, so before that, let's say Ig2 be the gate current of the thyristor 2. So friends, if I switch on the thyristor 2 after a specific period of time T2 say, let's say Ig2 be the thyristor current across the second thyristor. So now friends, I would like to show the diagram again just to be clear about the thyristor 1 and thyristor 2. So friends, here this is thyristor T1 and this is thyristor T2. Now let's draw the gate current of the thyristor T2. So the thyristor T2 is responsible for the negative half cycle and the thyristor T1 is responsible for the positive half cycle. Let's say friends, so this is the, if I draw a graph between the thyristor gate current and time, let's say this is Ig2, which is the gate current across the thyristor 2, and this is the time axis. So now let's say at this point of time, so let's say at this point of time I'm switching on the thyristor T2. So Ig2 will be the gate current that will be flowing across the thyristor. Let's say this is Ig2 for this specific cycle. Now friends, if I talk about the output voltage, how does it look like? So let's draw the waveform of the output voltage. this is time. Now friends, the output voltage will be appearing when the thyristor conducts. That means from this point to this point there will not be any flow of electric current through the thyristor. That's the reason you cannot see any output voltage. Let's say this point here is pi and this would be 2 pi. Now friends, let's draw the output voltage waveform. So the output voltage will look like, from here to where there is no voltage waveform that will be appearing across the output, but here as the thyristor started conducting, the voltage will be looking like this. As you all know, thyristor will stop conducting during the second or during the negative half cycle. I'm talking about thyristor T1, which only allows the flow of the positive half cycle, or which only allows the flow of electric current during the positive half cycle of the input sine wave. So now friends, again the second would be starting from here. Because of thyristor T2, again there will be a output voltage because the thyristor T2 also conducts. That's the reason the direction of the electric current during the positive and the negative half cycle is the same, because both the thyristor conducts during the positive and the negative half cycle respectively. So friends, if you can see, the final output waveform will look like this. So this will go a bit further because of the discharging nature again. So this will be the final waveform. Again here thyristor T2 is conducting because we are applying a gate current or a gate voltage to the thyristor T2. So it will again look like this. So friends, I would like to summarize again the waveform of output voltage. Here, if you can see, this is alpha again. So friends, as you all can see, from 0 to alpha, as nothing is conducting, thyristor T1 will be conducting because we are applying a gate voltage to the thyristor gate terminal. So we can see the output waveform. So it will just cross pi, and at a point this it will stop conducting because the negative half cycle started. Now again, from this point to this point, output voltage will not be appearing because no thyristor conduct the electric current. Now again, at this point, again you can see the waveform of the output voltage because thyristor T2 is switched on now just by applying a gate voltage to the thyristor T2, and so on and so forth. Now friends, let's talk about the output current, how the output current look like. So friends, let's compare the output voltage with the output current. So first thing which I am going to draw is the output voltage. Let's say this is the time axis, and let's say this is the output voltage axis, and let's say this is the output current, and let's say this is the time. Now as we all know, which we already draw earlier, the output voltage waveform, it looks like this. So let's say this value be pi and this value be 2 pi, and this is alpha and that is beta. So friends, here the graph will be looking like this, but before I draw the output current, I would like to show you all the graphs all together in one slide so you can literally compare the graphs. So friends, here you can have a complete overview of all the waveforms. So let's say this is the first graph which you already saw earlier, VAN and VBN, which are the two peak voltages. IG1 be the thyristor gate current, this is IG2, this is the output voltage waveform which we clearly saw how does it look like. And let's talk about the output current I0. If you can see friends, whenever there is an output voltage, the output current starts slowly rising because of the inducting nature of the load. Because of the inductive nature of the load, there is a tendency of inductor which do not allow a sudden change of electric current. That means it will allow the flow of current through it in a slow pace. So friends, here is the output current, and it will start slowly increasing and it will start slowly decreasing, and whenever there is no output voltage, there will not be any output current. Hence, again the same process continues. Now friends, hope you understand the flow of electric current and how does the output current waveform look like. Now let's talk about the thyristor voltage. Now friends, let Vt1 be the thyristor voltage, and if we draw a waveform between thyristor voltage and time, so this is the time interval for all the graphs. So whenever there is no output voltage, that means the thyristor blocks the voltage applied to it. It is in a forward blocking mode. So the thyristor voltage will look like this. This portion will be appear across the thyristor. Again, from this point to this point, the output voltage clearly appears. That means the thyristor is not able to block the output voltage. That means there will not be any voltage across the thyristor. Again, from this point, or say from this point to this point, again there is a thyristor voltage because this is blocking the negative cycle of the input sine wave, and so on and so forth. So friends, this is the entire graph in a single page so that you can literally compare and you can understand how does the entire RL load functions, or how do we get the waveform and how does it look like whenever an RL load is applied across a full bridge or across a midpoint rectifier. So friends, if you see here, there is a very nice phenomena. Whenever an electric current flows through an inductive load, either it flows in a continuous conduction mode or it flows in a discontinuous conduction mode. So what is a discontinuous conduction mode? So friends, if you can see here, from 0 to alpha, the output current or the current through the RL load does not flow, and from alpha to this point we can see a clear output current through the load. But again, from this point to this point, the output flow, the current starts flowing in a continuous manner. That means if there is no discontinuity in the flow of electric current, that means it's called continuous conduction mode. That means the current is being conducted continuously. So we will be talking about these two phenomena in detail in some time. Now friends, let's talk about what will be the value of the thyristor voltage. So you can see, let Vt1 be the thyristor voltage across the thyristor 1. So Vt1 will be equal to VAN plus V naught. Again, V22. Vt2 is the thyristor voltage across the thyristor 2. So this will be equal to VBN plus V naught, as we all saw that. Now friends, let's talk about the discontinuous conduction mode. Now friends, the discontinuous conduction mode will occur whenever omega t lies between 0 to alpha. So as we all know, V input is equal to Vs sine omega t. So when we are talking about the discontinuous conduction mode, that means, so there are different points of a discontinuous conduction mode. So those are, so in a discontinuous conduction mode, VAN is positive and VBN is negative. The next point would be, none of the SCRs are triggered. As none of the thyristor conducts, that's the reason we are not getting any output voltage, hence not any output current. Now friends, the third important point would be, the switching voltage Vt1 will be equal to VAN plus V naught. As you all can see friends, the thyristor 1 voltage or the switching voltage of the thyristor will be equal to VAN plus V0, where V0 is the output voltage and Vn is the input voltage. Now friends, let's talk about what happens when omega t lies between alpha to beta. Whenever omega t lies between alpha to beta, there are some points that is needed to be remembered. Let's talk about from omega t is equal to alpha to beta. First point would be at omega t is equal to alpha, T1 is in forward blocking mode. That is the reason whenever or until T1 or until omega t reaches to alpha, the thyristor blocks the entire input voltage applied across it. Now, the second most important point would be when T1 is on, so I'm mentioning T1 is equal to on, so then the current flows in the upper half of the transformer. Now friends, the next point would be when T1 is on, T1 acts as a short circuit that, as we all discussed in the earlier lectures, whenever thyristor is turned on, that means allows the flow of electric current completely, so this is short circuited. Now friends, let's talk about what happens to the inductive load. So friends, inductive load current rises slowly because, as we all know, inductor never allows a sudden change of electric current through it. So whenever you apply a change, or in this case the current will rise slowly and this will fall slowly. Now friends, let's talk about what is continuous conduction mode. So now if we draw the entire waveform due to the continuous conduction mode, which I already explained in a very briefly, now let's see how the waveform look like. So friends, here if you can see, I naught is in continuous conduction mode. That means there is no time when either of the thyristor T1 or T2 is off. That means T1 and T2 both are working at a time. That means T1 or T2 or T1 and T2 both are switched on in the entire operation. That's the reason the current is never going to zero. So here friends, if you can see the current, so if I start from this point, current slowly rises, again slowly falls, but it never goes down to zero. At this point there is specific positive value of electric current across the load. Again the same process continue. So that's called continuous conduction mode. The load current never goes to zero if an inductive load is connected. So the current through the output whenever an inductive load is connected, so the current never goes to zero in a continuous conduction mode. So friends, this is all about the entire graph whenever the mode is a continuous conduction mode. Now friends, let's talk about some points which will be explaining exactly what is continuous conduction mode. So friends, the first point would be T1 and T2 conduct at the same time. As I already mentioned earlier, none of the thyristors are off. Both are working parallelly at the same time. Then when T1 conducts, VAN appears, so which you already saw that. When T2 conducts, VBN appears across the load. When T1 is on, VT2 will be equal to twice of VBN. And when T2 is off, VT1 will be equal to twice of VBN. So here friends, when T1 is on, VT2 will be equal to twice of VBN, and when T2 is on, VT1 will be equal to twice of VAN. So friends, let's calculate what exactly will be the value of V0, which is the output voltage. Now friends, as we all saw, the output voltage appears across the load during the time alpha to pi plus alpha, because this is the only time when the thyristor conducts. So I can say 1 by pi in the integral, the limit would be alpha to pi plus alpha Vm sine omega t dt. So this, if we simplify this, this becomes Vm by pi minus cos omega t alpha to pi plus alpha, which finally becomes, so the output voltage will be 2 times the maximum input voltage divided by pi into cos alpha, where alpha is the conduction angle of the thyristor. Now friends, let's talk about one more parameter. Let's talk about the root mean square value of the output voltage. So you all know the formula for the root mean square value. So we already have discussed and we already tried to find out what will be the root mean square voltage whenever the diodes are connected in place of the thyristor. Now in the same way, we will be calculating the root mean square voltage value of the output voltage. So friends, here let's say V naught RMS be the root mean square output voltage, so which will be equal to, so friends, the root mean square output voltage will be expressed as this. So if we simplify this further, we will be getting, so the final value of the RMS value of the output voltage will be equal to 1 by root 2 times the maximum peak voltage. So this is the final result, friends. So friends, in this video we talked about how RL load affects the waveform of electric current, the value of electric current, the waveform and the value of output voltage. We calculated the value of the output voltages along with the root mean square value of the output voltages, and we saw the graph how the output voltage fluctuates with time and how the output current fluctuates with time in two different modes. One is discontinuous conduction mode and one is continuous conduction mode. So we saw two modes of operation, continuous and discontinuous conduction mode. So friends, thank you so much for watching this video. Please subscribe to Ekeeda and please stay tuned with Ekeeda. Thank you so much.